So last time we finished section 6.3. Let me start section 6.4. Matrix inversion. So first off, recall from the last section that matrices and let's say over some ring form a multiplicative group. And they also form an additive group. In that, say over any field F, they form a vector space over that particular field. And n by n matrices, let's say over a field, they form a non-commutative ring. So the problem with this is that even if you have n by n matrices, you can multiply n by n matrices together, but you don't necessarily have a inverse. So let's recall the identity matrix. Let's call it I. This will equal and this is for ij going from 1 to n, where this is equal to 1 if I equals j, and it's equal to 0 otherwise. And of course here, I goes from 1 to n, and j also goes from 1 to n. Okay, so that's the identity matrix. Now, we will say that a matrix B, maybe I should write this down a little further. Is the inverse, well, non-singular matrix. A matrix A, and suppose that it's a n by n matrix, a square matrix, is said to be non-singular, if there exists some matrix B, another M by N matrix, such that if you multiply them together, you get the identity matrix. So we call this matrix B the inverse of the matrix A, and is usually denoted by this little superscript here. Okay. Sorry, I was just trying to check to see if people were joined at a different website. So I was just checking. Okay, so so in general, the strategy for determining the inverse matrix. So let's see the strategy. Well, first off, note the following, I guess. Well, let's call it X. If AX equal B, then multiplying both sides of my equation by A inverse. Please note that this is not necessarily commutative, and so because of that, I have to be careful what side, the order of multiplication. So, well, A inverse times A, if it exists, then it's equal to the identity, but the identity times anything is just itself. So the strategy for determining the inverse matrix, the formula for the inverse matrix, is, well, you just try to solve the equation AX equals I, in which case you do it as a augmented matrix, and then multiply by A inverse. So meaning you perform a whole bunch of row operations so that now you have transformed this A into the identity. And then what you get on the other side is the inverse. And that is the strategy. You just perform all of these row operations until you get that. So let me do on page 598. Let's say problem number 8. I want to find the inverse of the matrix 1, 2, negative 2, negative 5. So I want to figure out this inverse here. Okay, so what I'm going to do is the following. Let me augment this matrix by the identity. And so now I'm going to write it in a reduced row echelon form. Okay. And so let's pivot. So the first row is going to stay the same. Here, wait 1 second. Let me just check. I'm checking to see if somehow people are joined at a different location. So just wait 1 second. I'm trying to log in using a different computer. So I'm doing more than one thing at the same time, just to check to see why no one's here. Okay, so it is 272537623. Okay, let's see what happens. ID is not valid. Oh. Two seven. Okay, well, then there's something wrong with that ID. Okay, I'll have to see. Well, luckily I'm recording this, so somehow that could be why no one's around. Okay, so at least you get the recording. Okay, so let me pivot this. So 1, negative 2, 1, 0. Let's take row 2, subtract from it 2 times row 1 to give me a new row 2. Okay, so 2 minus 2 times 1, 0. Negative 5 minus 2 times minus 2, so 4 minus 5, negative 1. 0 minus 2 times 1, negative 2. 1 minus 2 times 0 is 1. Let me pivot. So the first thing I'm going to do is I'll multiply this row by negative 1 to get a new row 2. And then let me multiply this new second row by 2 and add it to the first row to get a new first row. So 1 plus 2 times 0, 1. Negative 2 plus 2 times 1, 0. 1 plus 2 times 2, 5. 0 plus 2 times negative 1, negative 2. And so This says that the inverse is 5, 2, -2, -1. So that is the inverse of this matrix. Okay. Let me use this to solve an equation. And so this is particularly nice when, this occurs a lot of times, and say this will be a fixed matrix. Maybe it's involving some industry or something, but these will be variable. So it could be that you're trying to solve a whole system of different systems of linear equations, looking like this. So you wouldn't want to have to solve all these many times, but it turns out that all you'd have to do, so suppose you had a whole bunch of these to solve, then you just have to compute the inverse of A, and then just keep multiplying it by this new matrix, maybe for your what your buyers want to buy. Okay, so that will simplify solving these multiple systems of linear equations. Okay, so let me do problem number, I don't know, let's say, maybe I'll do a 3 by 3 in this case. Let me do problem number 32. Minus 2x plus y minus 3z equals 5. 2x plus 3y equals 1. X plus z equals 5. Okay, so let me solve this. Actually, let me rewrite this so it'll be a little bit easier for me to solve. And so, let me write it as follows. Let's do x plus z equaling 5. Just interchanging the first and third lines. Oh, by the way, I made an error. Guess I'm trying to do too many things at the same time. So it's equal to 5, 1, and -2. So the last equation was equal to -2. So 2x plus 3y equals 1. Okay, so now let's try to solve this system. And so let's just try to determine. So basically, this is going to be of the form ax equals b. And so I'm just going to try to solve it using the fact that all I need to do is determine the inverse of this matrix A. And so I have here a 1, 0, 1, a 2, 3, 0, a negative 2, 1, negative 3. Let's try to find the inverse of this coefficient matrix here. So let me input on the right-hand side the identity. So let's pivot. Let's multiply. So the first row I'm going to keep the same. For the second row, I'm going to do the second row minus 2 times the first row to give me a new second row. 2 minus 2, 0, 3 minus 0, 3, 0 minus 2, negative 2, 0 minus 2, negative 2, 1 minus 0, 0 minus 0. Let's get a new third row by adding twice the first row to get a new third row. 2 minus 2, 0, 1 plus 0, 1. 2, negative 3 plus 2, negative 1. 0 plus 2, 2. 0 plus 0, 1 minus 0, and 1 plus 0. Okay. And so let me interchange the second and third row. So I have a 1, 0, 1, 1, 0, 0, interchanging 0, 1, negative 1, 0, 1, 2, 0, 1, interchanging the second and third row. And then for the third row, I'm going to want to make this element 0 because I'm pivoting. So I'll take the third row, subtract from it 3 times the second row to get a new third row. Okay, so 0 minus 0, 3 minus 3, 3 minus 2, negative 2 minus 6, 1 minus 0, 0 minus 3. Okay, and lastly, let's pivot on this last guy. Okay, so actually I was sort of pivoting on that, I guess, after I interchanged it, so maybe I'll use that notation. Okay, so now I have the last row, 0, 0, 1, negative 8, 1, negative 3, let me add row 2 plus row 3 to get a new row 2. 0 plus 0, 0 plus 1, 1 minus 1, 2 minus 8, 0 plus 1, 1 minus 3. Let's subtract R1 minus R3 to get a new R1. 1 minus 0, 0 minus 0, 1 minus 1, 1 minus a negative 8, 1 plus 8, 0 minus 1, 0 minus a negative 3. Okay, so this says that A inverse is just 9, negative 6, negative 8, negative 1, 1, 1, 3, negative 2, negative 3. And so my solution is just A inverse B. So 9 minus 6 minus 8, negative 1, 1, 1, 3, negative 2, negative 3, times, in this case, it is negative 2, 1, 5. So let's multiply that out. 18 minus 1, 17, plus plus 15 minus 18. Minus 18 plus 1 is minus 17, plus 15 is minus 2. Oh, why did I just... Minus 18 minus 1 is minus 19, plus 15 is minus 4. 8, 12, plus 1 is 13, minus 10 is 3. 16 plus 1 is 17, minus 15 is 2. And so I get the following. X is negative 4, Y is 3, and Z is 2. And that is the solution to my system of linear equations. Okay, let me do, I guess, one more of these. Okay. Let me do problem number, let's say, 44. Whoa, 43, because that's a weird one. So let me do problem 43. So problem 43 says let A equal negative 1, 1, negative 1, 1. It says show that A squared is 0. So this is kind of weird. So let's look at A squared. So A is not 0, but A squared could be 0. Negative 1 times negative 1, so let's figure out this element here. So negative 1 times negative 1 is 1, minus 1, 0. 1 minus 1, 0. Negative 1 plus 1, 0. Oops. Didn't mean, I was pointing, not trying to erase. But I guess I erased. I'm doing this last one. Negative 1 plus 1, 0. So you notice that A is not the 0 matrix, yet a squared is 0. Okay. And that's just sort of that can certainly be possible. Um, okay, so that really finishes off section 6.4. Hmm. Let me go on to section 6.5. Determinants. Okay, so um, let me give you, I guess, the definition of determinant. Well, no, let me give you first. So a determinant is a function from square matrices to whatever field we're talking about. So usually it's from uh, square matrices with real coefficients to the reals. Okay. So first off, uh, before I give you the definition of determinant, let me give you some special cases. So first, special cases. Oh, and also, instead of writing DET, a lot of times we just instead of putting the brackets around the matrix, we'll just use straight lines. So it almost looks like an absolute value. When we do that, we're saying find the determinant. So instead of saying determinant, I'll say, well, A, B, C, D, and I'll put a little line. So actually, so instead of saying this, of course, I'll use the notation. Ugh. I'll use the following notation. A, B, C, D. Okay, so now the special case for 2 by 2 is the following formula. It's just equal to A times D minus B times C. Okay. Next, let me give you a special case for 3 by 3s. 3 by 3 case. Again, this is some special case. A, B, C, D, G, H, I. It will equal A, E, I plus B, F, G plus C, D, H minus G, E, C minus H, F, A minus IDB. Okay. Now, I can give you some ways to remember this. So, ways to remember two by two, 3 by 3 case. Please note these only work for 2 by 2 and 3 by 3 cases. So you would multiply, keep the same sign, multiply this way, subtract. And that's how you get this formula. Or for the 3 by 3 case, you would repeat the first 2 columns, and you would multiply this way. Oops. Keep the same sign. Multiply this way. And change the sign. So that's ways to remember the 2 by 2 and 3 by 3 cases. Note that these tricks do not work for the 4 by 4, 5 by 5, etc. cases. So it only works for this 2 by 2 and 3 by 3 case. So the minor and the cofactor. So the way that we deal with the higher order cases is we look at minors and cofactors. And so the minor of Aij for the matrix Aij. Now, bad notation, but here Aij, the i's and j's are arbitrary, and this is a n by n matrix. They're arbitrary numbers. I is 1, 2, 3 up to n. J is arbitrary 1, 2, 3 up to n. Whereas this is some fixed Aij. So the minor of this fixed Aij is denoted by Mij. Not to be confused with that. M. And this is the n minus 1 by n minus 1 matrix formed by deleting the ith row and jth column of this matrix, A or whatever. The cofactor Aij is denoted by, of course, of this matrix. Is denoted by Cij and is equal to -1 to the power I plus j mij. So it's just a up to sign. It's just the minor. Okay. Then it turns out that the determinant of some matrix or maybe I'll write it this way. That this determinant here is just equal to the sum. Oh, I see. Here, wait, let's write it this way. So the determinant of A, where A is equal to the matrix Aij, is just the sum. And you can do it either over a row or a column, doesn't really matter. I'll probably do this over a row. Oops, I forgot to write Aij. And let's do it, well, let's say for a row. So it will be the sum of a whole bunch of determinants that are of size 1 less. Okay. So that's a very important result that we'll be using for larger, to determine these larger matrices, the determinant of these larger matrices. Next, notice that maybe they called it a theorem here. If every entry in a row or column, doesn't really matter, of a square matrix is 0, then its determinant is 0. So if you happen to have a row or column of all zeros, then you know that the value of its determinant is 0. Uh, Now, the effect of row and or column operations on the value of a determinant. So even though we usually do row operations, again, as I always said, we could do column operations. Okay, so first, if you interchange rows, and so that row, you now have a new matrix, but with the rows interchanged, then, so let's use the following notation. Let A be the original matrix. Of course, it's an n by n matrix. And B be the matrix after the following row or column operation. Then, if I interchange two rows, then the determinant of B is opposite the determinant of A. So interchanging two rows or columns will cause the determinant to change sign. Next, if you multiply a row by some constant, then this will multiply the value of that determinant by that value. Similarly, if you do it for a column. And lastly, oops, if I pivot, so I do Ri plus K Rj gives me a new Ri, then does not change the value of the determinant. So if you do a pivot, this does not change the value of your determinant. Using the fact from above, that if you have a whole bunch of zeros, it makes it 0, the value of your determinant, then you should try to pivot so that you have a whole bunch of zeros. That'll also make all the, oh, and I should say it both ways, just in case. You could either do it row or column. So even though I said it, maybe I should write it. Okay, so let's do some examples, and then maybe I'll give you the, oh, of course that's also, let's do some examples. Well, maybe I will give you that one little fact, which is theorem. If A is a square matrix with two identical rows, or columns, then the determinant is 0. And of course, we could have already seen that because you just pivot, and that would have made it all zeros. So we know that it'll be 0. Let's do on page 600. And 10. Let's do a few examples. Say problem number 8. -3, 2, -6, -5. So this is going to equal -3 times -5 minus 2 times -6. So that's 15 plus 12, 27. So the value of this determinant is the number 12. So you notice that you're going from a matrix and you're just getting a real number. Let me do, by the way, in this case, they give me actually a slightly different definition, but, and so I can slightly change this. Okay. This is actually the determinant. They wrote it this way. You can do it either way. Denoted by Mij is the determinant of a n minus 1 by n minus 1 matrix formed by deleting those. Okay. They put the determinant inside the summation. Let me do problem number 20. Oh, wait. Let's do one of these. Let me do problem number 11. M21. Okay, for the following matrix. Suppose I have 1, 4, minus 7, negative 2, 5, 8, 3, negative 6, negative 9. Okay, so it says here to find a sub 2, 1. Okay, so let's find this minor. So what I'll do here is I'll get rid of, the second row in the first column. And so let me do that. Second row, first column. So this becomes the determinant of, well, negative 2, 3, 8, negative 9. And so negative 2, the determinant of this 2 by 2, is equal to negative 2 times negative 9 minus 8 times 3 wait 1 second. That was just a typo, I noticed. So this is equal to negative 18 minus 24, which is minus 42. Let me do problem number 15. C21. Okay, so I can think of this as doing it either of two ways. One, using the fact that it's equal to this. And so C sub ij, this cofactor, is negative 1 to the I plus j times the minor m sub ij. And so this is equal to a negative 42, which is positive 42. Or another way of thinking about this, always start out with plus and just keep alternating signs. If you do that, then you can figure this out also. And so plus minus. So in this case, it changes the sign from negative 42 to positive 42. Okay. Lastly, let me do problem number 30. Which is negative 1, 2, 1, 2. Okay, negative 1, 2, 1, 2, 3, 1, 3, negative 1, negative 2, 0, negative 2, 0, 5, 1, 5, -1. Okay, so let me just pivot on this guy. The only way I can evaluate this to determine it is by doing the cofactor expansion. I do not have any of those easier sort of special cases to use on this, so I'm going to have to do it the other way. Okay, so let me pivot on this guy, and let's try to make this whole column here uh, zeros below this guy. So let me do row 3 minus row 1 to give me new row 3. But everything else will stay the same. So -1, 3, -2, 5, 2, 1, 0, 1. So let's subtract. So there'll be a 2, 0. 1 minus a -1. 1 plus 1 is 2. 3 minus 3 is 0. -2 plus 2, that's 0. 5 minus 5 is 0. I could go along this now. And keep this the same. Okay, so now let's do a cofactor expansion along this column. Or I could do it along this row here, this third row, because all these have a whole bunch of zeros. I'll do it along the column, I guess. So it's going to equal plus minus plus -2 times. Get rid of this row in this column. So 2, 1, 1, 2, 0, 0, 2, -1, -1, minus, well, 0 times something plus 0 times some, again, cofactor, plus minus 0 times some other cofactor. So having a whole bunch of zeros here simplifies things. So I don't really have to worry about any of those. Okay, so let me evaluate this. So it's -2 times. Let me use the trick that I had from before. 2, 2, 2, 1, 0, -1, 1, 0, -1. So let me repeat the first two columns. And then let me multiply. This way, that way. And then this, and this. So I get -2 times 0. 2 times 0 times -1 is 0. 1 times 0 times 2, 0. Plus 1 times 2 times -1. So that's a -2. Minus 2 times 0 times 1, that's another 0. Minus -1 times 0 times 2, that's another 0. Minus a -1 times 2 times -1. Minus a -2 is plus 2. So the 2's cancels, you get 0. -2 times 0 is 0. So this the determinant of this 4x4 matrix is 0. Okay, so let me quickly give you the definition of the determinant. And so a permutation of an ordered list A, or S, let's say, is a bijection from S onto S. The symmetric group of n letters is the group, the set of all permutations of 1 through n with composition is the group operation. So all it means is that you just keep changing the order of all of these numbers 1 through n. And inversion so let, I don't know, pi be a permutation. Then let's say ij is an inversion if I is less than j, but the order here is reversed. So it's the number of times you reverse your numbers. Okay. So a determinant and let's say this is for real values. Let's do it. So the determinant is some function from these square matrices to the reals, defined by the following. The determinant of A is just the sum of -1 of these inversion pairs of the product of A sub I sigma I, where this inversion is the number of inversions of the permutation sigma. Okay, so that's the definition of a determinant. In general, we don't use that definition just because it takes forever, literally forever, to actually use that. So we use these other properties that I've given you above to actually calculate the determinant. I guess now the question is, why do we want to know this? So Cramer's rule. So suppose you have the following. Okay, and suppose I have n of these. So an1 x1, an2 x2, an3 x3, ann xn. Okay, so suppose I have an n by n system. Let A equal aij. and let A sub, I don't really care, xi equal where? Okay. Where B sub ij is equal to aij. Oh, maybe I should call it k. X sub k. Because that'll be better for my notation. Where if j is not equal to k, if j is equal to k. So where you replace your your kth column in this case, your kth column by the, oops, sorry about that, where you replace your kth column, I wrote the wrong thing, by the non-homogeneous part of the equation. So then, if this determinant is not 0, oh, I should have let it be the determinant of this, and the determinant of that. Okay, so then if a is not 0, then that implies that x sub k is just equal to a x sub k over a. So if your coefficient matrix is non-singular, then you can actually determine the value of each of your, you can solve your matrix, your system of linear equations by just using this formula. Now, of course, this formula won't work if you have more than one solution or if you have no solution. Of course, those are the cases where the determinant of the coefficient matrix is 0. Okay, so let's do some more problems. Let's say no, actually, maybe I should tell you about that. So another reason why you might, so that's Kramer's rule. That's another good thing about determinants is that you can solve equations using a formula. Now, of course, in all reality, it's not very practical to use determinants to solve equations because determinants in general are very labor intensive. It's very difficult to actually solve, to actually calculate these determinants. The two-point form for the equation of a line. Well, the 2-point form for the equation of a line can be written as a determinant. And so it's just the determinant of x, y, 1, say x1, y1, 1, x2, y2, 1, equaling 0. That is the 2-point form for the equation of a line. Next, it turns out that the determinant is the signed area. Signed, well, let's call it hypervolume of the parallelepiped determined, let's say by the rows or columns of the matrix from which you're calculating the determinant. So really, a determinant is just the volume up to sign of what's inside of your determinant, considering those as vectors. So you can use this to find the area of a triangle. If you just happen to know the location of the vertices of your triangle, so let x1, y1, x2, y2, x3, y3 be vertices of a triangle. Then the area of a triangle will just be 1/2 times the determinant. Let me write it as determinant because I need absolute value of the determinant of the following: x1, y1, 1, x2, y2, 1, x3, y3, 1. And if you just take the absolute value of that, because again, it's the signed area, so it could be plus or minus. So pick it so that it's positive. Okay, let's do an example on page 611. Problem number 40. X minus 5y equals negative 6. 3x plus 2y equals negative 1. Okay, so let's use Cramer's rule. So Cramer's rule says, well, a is a determinant of 1, 3, minus 5, 2. Well, let's calculate this, because if it's 0, then I can't proceed anyway. And so let's calculate what this is equal to. 1 times 2 minus 3 times negative 5. So this is 2 plus 15, 17, which is non-zero. Good. So I can proceed. So let's proceed with Cramer's rule. So a sub x, replace the x column, the first column, by the right-hand side of the equation, by the non-homogeneous part. So I get negative 6 times 2 minus a negative 1 times negative 5. Negative 12 minus 5 is negative 17. Let's do a sub y, which is 1, 3. Replace the y column of the coefficient matrix by the non-homogeneous part. So 1 times negative 1 minus 3 times negative 6. Negative 1 minus plus 18 is 17. So this says that x is a sub x, negative 17 over 17, negative 1. Y, a sub y over x, over a. 17 over 17, 1. So this says x is negative 1, y is positive 1. And that is the solution of my equation. So the good thing about this is that it's a formula, and you just plug into that formula. Of course, the bad thing is that, it could take a while for you to calculate each of these determinants. So it's not necessarily the fastest route. As a matter of fact, if you look at, let's say Google, which has probably a 500 billion by 500 billion matrix, a system of linear equations that they're looking at. If you try to solve that system of equations, it would take you, using the definition of determinant, well, let's just say you were looking at a 40 by 40 determinant, and you use the definition that I gave you. On a supercomputer, it would take the age of the universe to compute that. Who knows how long it would take you to do the things that Google does, which they do in a millisecond. Of course, they're actually not solving the equation, they're doing an approximation, and they're actually finding the largest eigenvector. And so they're looking at something else, but something very close. It's something similar to solving this system. Okay, 52. But of course, they only do an approximation, because you don't have to be accurate, completely accurate, but you should be fast. So speed does matter. Okay, so use determinants to write an equation of the line in standard form that passes through the given points. Okay, so let's find the equation of the line. So x, y, 2, 3, 6, 8. Okay, so let's just use that trick from before. X 2, 6, Y 3, 8. So let's multiply. Multiply. Subtract. Okay, so we have 3x plus 6y plus 16 minus 18 minus 8x minus 2y equals 0. Minus 2y. Okay, and so let's see, 3x minus 8x is a minus 5x. 6y minus 2y is 4y. And then minus 2 equals 0. And it says in standard form. Okay, so let's multiply everything by negative 1. And subtract 2 from both sides. If you recall, for standard form, since there's an infinite number of differing equivalent standard forms, we pick the one, if possible, where the coefficient in front of the x term is non-negative, where each of the values of the coefficients are integer valued, and where the greatest common factor and where each of these coefficients are relatively prime. Okay, let me do problem number 56, which says, suppose actually let me do 57 because let me do 57. I'm given P, Q, R. Find it using determinants. Use determinants to find the area of each triangle with the vertices at the given points. So I have these 3 vertices. Let's find the area. So first let me calculate the determinant. And again, I'll just use that trick where we rewrite the first 2 columns, multiply, multiply, and so this is equal to 16 plus 0 plus 200 minus 0 minus 40 minus 30. And so this is equal to 16 plus 130, 146. So the area of my triangle is going to be 1/2. Well, I don't have to make it positive. It's already positive. 146. So that's equal to 73. So the area of my triangle is 73 square units. Let me do, and that's, no, I guess that's it. So that's finishes off section 6.5. Let me go on to section 6.6. Partial fractions. So the idea of partial fractions is I want to write any sort of any sort of rational function any rational function to be in the following form. So it'll be some polynomial following type of form. Obviously, it won't be, this is a following form like this example. So it'd be like some polynomial plus some easy fractions. So of the form, you know, so I want some polynomial, and then these fractions. So what you notice about these fractions is they aren't like, the denominators is not the product of a whole bunch of factors. They're either linear factors or powers of linear factors or possibly a quadratic factor. And that's it. So each of these, you know, so such as I would like to write something like, say, well, first off, I guess what I'll say is that if I have a rational function, certainly I can divide it and I'll get a polynomial plus some remainder. So let's only look at the remainder sort of thing. So that this remainder term will be some polynomial of lesser degree over another polynomial, which will be have a higher degree. So suppose I have something looking like 8x squared plus 9x plus 2 over x plus 1 squared. I want to write it as something looking like this. Okay. So what you notice is that if you have a polynomial that is of the following form. So let P of x and Q of x be polynomials. Oh, and let's say with real coefficients. Okay. And suppose the degree of P is less than the degree of Q. If it's not, then you just divide and look at the remainder term. Okay. Then I can always factor over the reals as some constant and let's say to some power. So a whole bunch of linear terms to maybe some power, and a whole bunch of, I don't care, A, B, let's call them C's now. I call those N's, so how about M's? So you can factor any polynomial into linear terms, quadratic terms, two powers. Okay. So then P of x over Q of x can be written as, well, you can deal with each of these terms as follows. You'll just have n one of those. Why did I change the letter? Don't know. Okay. And then, of course, you'll have for each of these up to n sub whatever. And then you'll have, in addition to that, these, maybe call them b's. and C's because I want. And I call them, make sure that's equal to, looks like a big C. C1x squared plus D1x plus E1 plus, and then you'll have M1 of those. I called it M1. And of course, you'll have however many of those there are. Okay, so they'll just look like a whole bunch of linear terms to, oops. I wrote it to the wrong powers. I didn't write the powers down, of course. Plus, so you'd have all of these terms here, and they're all sort of what you notice is that the numerators are all really nice, and the denominators are all sort of just linear terms to powers or quadratic terms to powers. Okay, so the way you determine the coefficients, well, you'll have a whole bunch of equations, and you can just set the coefficients equal and solve for it. So it's solving for undetermined coefficients. So let me do on page 620 an actual problem to show you how this works. Okay, let's say problem number 6 on page 620. So suppose I have the following. Five x plus 21 over x plus 7. So notice the degree of the numerator is 1, degree of the denominator is 2. After I've done that, I really don't care about the numerator. I just look at the denominator. Well, I have a product of two things, x and x plus 1. The numerators must be things that, well, if this is linear, then they have to be constants. Maybe I'll call it a and b. So now, let's simplify this. Well, multiply and divide. Multiply, divide by x. Multiply and divide by x plus 7 to get a common denominator. So you get ax plus 7a plus bx all over x plus 7. And so you notice that we have just grouping all the terms involving x. I have the following. So now I must have that a plus b is 5 and that 7a must be 21, just equating the coefficients. Since the denominators are equal, the numerators must be equal. And since this is true for all x, then each of these coefficients must be equal. So from here, I get, well, a must equal 3. 21 divided by 7 is 3. And then, well, 3 plus b is 5, so b is 2. Therefore, I have rewritten 5x plus 21 over x plus 7 in a much simpler form. It's now in the form 2 over x plus, I'm sorry, that's a was 3. 3 over x plus 2 over x plus 7. And actually, if we'd done this before, they should have actually done this before, this would have actually helped us when graphing rational functions, because then that would have given us the asymptotic behavior of each of these. Okay, let's do problem number 28. So problem 28, 3x squared, no, 3x cubed, sorry. 3x cubed plus 5x squared plus 3x plus 1 over 28. Why am I looking? I'm looking at two different problems. Okay, sorry. 28, 3x squared plus 13x plus 20 over x cubed plus 4x squared plus 4x. So I really only care about my denominator. Notice that the numerator has a degree of 2, denominator has a degree of 3. So the thing that I'm concerned about would be the oh, okay, so someone is saying that the website isn't working. Okay, so I will send it to you. I will send you the thing when I am done. Okay, the recording when I'm done. Okay, so I have here, I don't care about the numerator. All I care about is the fact that the degree of the numerator is less than the degree of the denominator. That's fine. Let's factor the denominator. I can factor out x, but then I can factor this out some more. This is just x plus 2 quantity squared. And so now I get that 3x squared plus 13x plus 20 all over x plus 2 quantity squared. I should be able to write it as something involving x, something involving x plus 1, x plus 2. So notice I'll just write it just like before. If I have factors, I can just write it at these factors. But if it happens to have a power, I have to write all the powers down. And so now the numerator will have degrees less than the denominators. So this, I call this A, B, and C. Each of these are going to be, I'm saying that the degree of the numerator is less than this guy, which has a degree of 1. So each of these are just going to be constant terms. Now, I can get a common denominator. So I can multiply this by x plus 2 squared, which is x squared plus 4x plus 4. I can multiply this by x times x plus 2, which is x squared plus 2x. And I can multiply this guy by x. Okay, so this is equal to, so I have that 3x squared plus 13x plus 20 all over x. X plus 2 squared is equal to, well, I have a common denominator, so let me just write them all over the common denominator, x plus 2 squared. So I have an a x squared, but I also have a bx squared. So it's a plus bx squared. I have a 4ax. I have a 2bx. And I have a 3cx. Plus, the linear term is only 4a. So let's equate coefficients. So a plus b is equal to 3. 4a plus 2b plus 1c is equal to 13. 4a is equal to 20. So 4a is 20, so a is 5. A plus b is 3, so 5 plus b is 3, so b is negative 2. And then let's see, the last equation is 4a, which is 20, plus 2b, which is 10, plus c is 13. So c is equal to 13 minus 30. Wait, b is not 5. b is negative 2. 16 plus c, 16, so negative 3. Sorry about that. So c is negative 3. I for some reason saw that both a and b were 5, but no. A is 5 and b is negative 2. So therefore, we have written this rational expression much nicer. 3x squared plus 13x plus 20 over x plus 2 squared. I can write it as a 5 over x plus b 2 over x plus negative 2 over x plus 1 plus c negative 3 over x plus 2 squared. And that is a much nicer and simpler way to write my rational expression. Let me do problem 38, which is the last of the differing forms. But the techniques are all the same. In the future, when you do these again, you'll have another concept. I gave it to you actually, the concept of a derivative of polynomials, the derivation of a polynomial, but I didn't give you some properties of them. So if you use some of those properties, you could actually simplify some of these calculations quite a bit. Also, another way of doing this is you could have just plugged in some easy values for x and determined equations. But so far they've been so easy, I didn't even have to do that. Let me do problem 38. Which is x cubed plus 3x squared plus 2x plus 4 over x squared plus 1, x squared plus x plus 2. So first off, I notice that the degree of the numerator is 3, degree of the denominator is 4. So this is the type that I can use my partial fractions on. It's a remainder. Now, x squared plus 1 is irreducible over reals. So it should look like something x squared plus 1. But notice this is of degree 2. So my numerator should be of degree 1. And my denominator is going to be, well, let's see, x squared plus x plus 2. That's also irreducible over the reals. The and so this should look like ABC plus D. Okay, so it looks something like that. So let me simplify this. Actually, let me move this out so I can multiply by things. So let me multiply and divide by x squared plus x plus 2, x squared plus x plus 2, and let's multiply and divide by x squared plus 1. Okay, so I can probably write it here. X cubed plus 3x squared plus 2x plus 4 over x squared plus 1, x squared plus x plus 2. I'll probably have to do this in 2 stages. So this is ax cubed plus ax squared plus 2ax plus bx squared plus bx plus 2b plus, let's write it all over the common denominator. Hopefully I can write it all down here. Plus cx cubed plus dx squared plus cx plus d. Just made it. Okay, so I have x cubed plus 3x squared plus 2x plus 4 over x squared plus 1 x squared plus x plus 2 is equal to a plus c x cubed, those are the only x cubed terms, plus a, b, d, x squared. Let me just check again. A, C, A, B, D. Let's look at the linear terms. So 2A plus B plus C x. Let me check. That's 2A plus B plus C. Okay, and then plus lastly 2B plus D. X squared plus 1, x squared plus x plus 2. Okay, so from here we get A plus C equals 1. A plus B plus D equals 3. 2A plus B plus C equals 2. 2B plus D equals 4. Not as many things cancel as before. Okay, so darn, that's a 4x4. Don't see anything obvious. Okay, so A, 2, no A's, no B, 1B, 1B, 2B, C, 1C, no C, 1C, no C, D, no D, 1D, no D, 1D is 1, 3, 2, 4. I may have to solve it like this. Okay, so let's pivot. And might as well do it anyway. It's good practice for what we're doing a few minutes ago. So I'll keep the first row the same. Second row, subtract the first row to get a new second row. Okay, so 1 minus 1, 0, 1 minus 0, 1, 0 minus 1, 1 minus 0, 3 minus 1. Okay, let's make this guy 0. So take row 3, subtract 2 row 1 to get a new row 3. 2 minus 2, 1 minus 0, 1 minus 2, 0 minus 0. Good. 2 minus 2. Okay. Pivot. So 1, 0, 1, 0, 1, 0, 1, minus 1, 1, 2. So let's subtract. So do R3 minus R2 to give me a new row 2. Row 3 to give me a new row 3. 0 minus 0, 1 minus 1, 1 minus 1, 0 minus 1, 0 minus 2. Make this 0. And so let's do R4 minus 2R2 to give me a new row 4. 0 minus 0, 2 minus 2. 2 plus 0. Okay. And 1 minus 2. And 4 minus 4. Okay, so if you interchange the second and third rows, third and fourth rows, it's in upper triangle form. So let's back substitute. So A, B, C, D. Negative D equals negative 2. So D equals 2. And then let's put that in this equation, even though I'm thinking of this as being the third equation, this third equation. So 2C minus D equals 0. So C equals 1. Okay. And then I have B minus C plus D equals 2. And so B is equal to 1. And I have A plus no B plus C is equal to 1. So A is 0. Okay, so I have the following. Oops. Oh, and I guess I have to... No, I can get rid of that. I'll just write at the very bottom. So I have x cubed plus 3x squared plus 2x plus 4 over x squared plus 1, x squared plus x plus 2 is equal to no x, no x plus 1b over x plus 1, x squared plus 1, plus abc, x plus d, 2, over x squared plus x plus 2. And that is your answer. So that finishes off section 6.6. Okay, let me go on to section 6.7. Graphs of inequalities. Okay, so first, standard form. So we're going to graph inequalities, linear inequalities, in two variables. Oh, and inequalities that aren't. Okay, so Standard form. This is for a inequality in two variables. It will look like a less than or equal to mx plus b. Y is less than mx plus b, greater than or equal to mx plus b, greater than mx plus b. Or, if you can't solve for that, for y, then it's x less than or equal to b, or, yeah, let's say b. X less than b, x greater than or equal to b, x greater than b. Okay? Okay, so let's do some examples on page 629. Let's do problem number 6. 4x minus 3y greater than 6. Okay. So let's subtract 4x. Divide both sides of your inequality by negative 3. So the inequality will switch. And so this inequality will have a dashed boundary line because there's no equal sign here. And since it's less than, this will be true below the graph of the boundary line. So let's sketch a graph of this. Oh, and note that for the boundary line, the slope is 4/3, and the y-intercept is negative 2. Okay, so the y-intercept is negative 2, and we have a slope of 4/3. So go up over 3, I guess. 1, 2, 3, up 4. 1, 2, 3, 4. So it should look something like this. And it is... Is there any way to move this guy? No. Okay. Is there any way to move that? Okay. I guess I'll have to just move it out the way for a second. Okay, so this is... No, I can still touch on that. I did. So this is going to be true below. And so the graph should look something like this. I sort of went over there, but... Okay. Okay, so the graph looks something like that. Of course, it continues on forever, but this is just sort of a more or less graph of it. Um, let's do problem 26. Oops. So suppose I have y less than 3x plus 2 and y is less than negative 2x plus 3. So if I look at the graph of this, well, for this first line, this first boundary line, the y-intercept is 2, the slope is 3, and there's no equal sign, so it will be a dashed line. So it'll look something like this. For the second line, and of course it's true below, so it's going to be true in this direction. Let's shade where it's true. Usually you shade where it's true unless you have to have so many of these equations, like 4 or 5 of them, where it's easier to shade where it's false. Okay, for the second line, the y-intercept is 3, the slope is negative 2, and so again it's dashed boundary line because the inequality here is less than, so it's true below. So again, it's true in this direction. And so if I look at where the overlap is, where all the arrows point, well, it's going to be true in this region here. And this is my solution. Oh, and I guess I really should have indicated that this is my solution. Oops. This is my solution. The region that I've shaded. Because it could be that the region that I shade is not the solution. Okay, let me do problem number 34. Y is less than or equal to negative x squared plus 4 and greater than negative x plus 1. So I notice that the first one is going to be a parabola. The first boundary line is a parabola. Whereas the second one is the boundary line is a line. And so let's solve this. All right, let's graph the solution. Well, the first boundary line is y equaling negative x squared plus 4. So 1, 2, 3, 4. It's a parabola that points down. So y-intercept at 4, vertex at 4. And so it looks something like this. Yeah, well, whatever. Okay, so it's very difficult to draw on this thing. Okay, let's see if I can actually do this. Okay, here, wait 1 second. Let's do this then. Okay, see if I can draw this. Get into a better position. So 1, 2, 3, 4. Good enough. I shouldn't put arrows since this is a boundary line. And it's true below. Okay. So it's true in this region. And I have y is equal to a negative x plus 1. So the y-intercept is 1, and it goes down at a slope of 1. And it is a dashed line since there's no equal sign. So it should look something like this. And it is greater than, so it points up. So it's true in this direction. So if I look at that, well, it's got to be true. Come on, there it is. So it looks like it's true over in this region. So this is my solution. Okay. Okay. So it's very similar to doing nonlinear as doing the linear ones. Okay. So that really finishes off section 6.7. Let me go on to section 6.8. Okay. Okay. So section 6.8. Linear programming. So in general, a linear programming problem will consist of some objective function So let's say it'll be of the form 3x minus 7y or something. This will be, and say you're trying to maximize, I don't know, say a profit. So this is your objective function. And you may want to maximize or minimize that. But it'll be subject to some constraints. So your constraints will be something like x is greater than 0, y greater than 0, and who knows, x plus y less than 20 or something. So these would be my constraints. And your constraints are going to form some sort of figure. This figure here will be some sort of convex polytope. Okay. Good. It'll be a simplex. It'll be something looking like okay. 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 Having trouble with the controls, obviously. Okay, so it will look something like, I don't know, maybe there. Okay. So this will be your constraints will cause this sort of region to be created, a feasibility region. And so you'll have some sort of linear constraint, which means that you'll somehow have these differing values, and you want to maximize along this. And so what you'll notice is that the maximum and minimum can occur only along the vertices. Of this simplex. Okay. Or possibly, of course, if it happened to be that your constraint equation and your objective were parallel to each other, it could be that it's maximized all along either a vertex or along one of the sides. Okay. So let's do on page 639. Let's do problem number 12. Maximize P, which has the form x minus y, with the following constraints. Y is less than 5, x is greater than 0, y is greater than 0. Okay, so let's look at this. So let's draw this. Okay, so I have here y is less than or equal to 5. 1, 2, 3, 4, 5. X is greater than 0. And y is greater than or equal to 0. So this is my feasibility region. X is greater than 0. Y is greater than 0. Okay, so turns out, that the maximum of this has got to occur along either one of these, along the boundary. So let's just say that the maximum must occur along the boundary. So let's look at this. Well, this is just, so if I look here, this p equaling x minus y is the same as, well, add y to both sides and subtract p. Y equaling x minus p. Okay. And so it just looks like a line having a slope of 1 and a y-intercept of p. So if I look here, looks like this. That's when p is equal to 1. p equals -1. Oops, oops. Of course I put in the wrong. That's 1. P equals 2. 3. No, that was right before, because that's a -3. 1, 2, 3. Okay. So here, if I want to maximize this, so oh, of course, I guess this can't be bigger than. Y's got to be less than that. Oh, and I forgot one other constraint, which is 5x, oops, 5x plus 4y is less than 20. Oh, okay. So there was another constraint, so this doesn't go off to infinity, so this doesn't become maximal. Here, wait. So I have here that y is less than or equal to -5/4 x plus 5. Ooh, okay, so that makes this region a little bit different because it doesn't go all the way out to infinity because of this constraint. It's less than or equal to that. So this is, ah, darn. Okay, so I'm going to have to erase this because the constraint doesn't go out to infinity. It could, but in this case it doesn't. I forgot one. I didn't write one of the constraints down. Okay, so so let's see. At 0, it's 5. 1, 2, 3, 4, 5. Oh, so it doesn't really matter. And it's 4. 1, 2, 3, 4. So my constraints look like this. Okay. Okay, so So the vertices are at 0, 5, 4, 0, and 0, 0. So let's figure out the value of P at each of those. Okay, so 0 minus 5 is negative 5. 4 minus 0 is 4. 0 minus 0 is 0. And I want to maximize it. And so the maximum of P is 4 at 4, 0. Sorry, I missed the constraint. Let me do problem number 20. Let's see if I write down everything. Okay, so you want to, problem 20, what do you want to do? Minimize. Okay. Minimize P, 20. Y minus 2x, subject to the following constraints. X plus y, x plus 2y, less than 4, less than or equal to 4. 2x plus y, less than or equal to 4. And x plus 2y greater than or equal to 2, and 2x plus y greater than or equal to 2. Okay, so these are strips, right? Because these are both the same. Oh, okay. So if I look at these, it says that x plus 2y is between 2 and 4, and 2x plus y is between 2 and 4. Okay. So let's look at this first equation. So I have let me write it this way. Subtract x from both sides. Divide by 2. And we also have the other equation constraints that 2x plus y is between 2 and 4. Subtract 2x. Okay, good. So I can draw these. So these are two little strips here. Okay, so the y-intercept's at, so let's do the first one. Y-intercept's at 1, and it's a slope of negative 1/2. And it's a line. And the other one is plus 2. And it's a line. Okay. Drew it too big. And then the other one was 2. And has a slope of 2, negative 2. Let's draw it bigger because my drawing is not good enough for the scale that I've drawn this thing. So 1, 2. 1, 2. Okay, so let's see. At 2, at 0, it's 2. At 2, it's 1. Okay. So it looks something like this. At it's 1. Then at 2, it's 0. So it looks something like that. That's these first two equations. So that's this first boundary line. And that's the second boundary line. Let's do the other one. It's still another 2. So at 2, it's 0. At 0, it's 2. And at 1, so so it goes like this. Okay. And it's at 4. Okay, and then it comes down, I don't care, it's from up here. And at 2, it's 0. Okay, so it's coming down parallel. Okay, so the feasibility region is in here. My feasibility region. Yeah. So here's my feasibility region. Okay, good enough. So this is 0, 2. This is 2, 0. Let's figure out where each of these are. So this is the line. Let's actually write each of these, what each of these lines are. This is y is equal to negative 1/2 x plus 1 plus 2. This is y is equal to negative 2 x plus 2. This is y is equal to negative 2x plus 4. Okay. So let's figure out where each of these 2 points are. And so let's set these 2 equations equal to each other. Negative 1/2 x plus 1 equal to negative 2x plus 2. Add 2x to both sides. Subtract 1. So x is equal to 3/2. And so y is equal to 1/4. 3/2 gives me no, wait. Okay, so wait. 2/3. And so that's equal to 1/3. That's equal to 1/3, 2/3. They're both 2/3. Let's check. And so that'll be 4/3 minus 6, 2/3. Good. So the point over here is 2/3, 2/3. Let's figure out the other point. So let's set -1/2 plus 2 equal to this other constraint, -2x plus 4. Add 2x to both sides. Subtract 2. So x is equal to 1/4. And y is equal to 4/3 gives you -2/3 plus 6/3 is 6/3 minus 4/3 is 2/3. And let's check if that works. So that's 12 minus 8/3. 12 is 4/3. Okay. And 6/3 minus 2/3 is 4/3. Okay, so this is also 4/3, 4/3. So now let's check. P at 2/3, 2/3. Okay, so P is, we're minimizing or maximizing, minimizing y minus 2. So y minus 2 times 2/3 minus 4 is minus 2/3. Let's plug in. Two zero. So it is 20 y minus 2x. So y minus 2x -4. Let's plug in. Oh, but it's parallel to that. Ooh. Okay, so let's check. Oops. That's, I did 2, so 4/3, 4/3. So it is y minus 2x is minus 4/3. And lastly, so I did those three. 0, 2, I didn't do 0, 2 yet. So it's y minus 2x is 2. And I want to minimize this. So the minimum when p is -4 at the point 2, 0. And that's your answer. There's also a something called a simplex method, which works with a tableau, something looking very similar to what we work with when we're dealing with Gaussian elimination. It's just we have to introduce some new variables, some slack variables, to make the constraint equations into equalities, where all the variables will then be non-negative, have non-negative values. And then you can optimize using this sort of technique, which is very similar to what we did when we were pivoting using Gaussian elimination. But really, that finishes off this section. 6.8. Which finishes off Chapter 6. So let me start Chapter 7, which is on conic sections. Section 7.1. Circles and the parabola. Well, chapter 7. Conic sections. And quadratic. Systems. So actually, before I do that, I'll sort of tell you what we're doing. So suppose we are very hungry and we want an ice cream cone. And suppose that we're extremely hungry. So let that ice cream cone go out to infinity. And suppose you are very, very hungry. So let's have one ice cream cone upon the other ice cream cone. So you'll have two cones attached to each other going out to infinity. Now, if I slice straight on this way with some plane, some blade in the plane, then this point of intersection here will be a point. If I go along this edge here, the point of intersection will be a line. If I go straight on, I'll do it yellow, then it will be these two lines. Yellow's a little hard to see, but it's okay. Purple. Let's go at a angle here, straight across. If I do that, then this point of intersection will look like a circle. If I go at a slight angle here, not quite straight across, then this will look like an ellipse. If I go at a angle here. Oh, let's do it this way. That's still an ellipse. Let's go. Okay. So I go at this angle here. Then this will look like a parabola. And suppose I go, well, let's do that one. That really weird pink, purple pink color. Let's go this like here and here. Then the intersection will look like this and like this. It'll be a hyperbola. So the conic sections are these above. So the conic sections. So these are slices of a cone. So these slices of a cone can be, well, I can slice it where I don't hit anything. So the empty set. A point, a line, or two lines even, a circle, an ellipse, a parabola, a hyperbola. So we've already really looked at the empty set, a point, a line, and two lines. So in this chapter, we'll look at the circle, ellipse, parabola, and hyperbola. Okay. So where would you see these? So where? Do the following. Take a martini glass, fill it with something, hopefully something that's nice and colored. And so if you look at it, well, initially you'll see a circle, slightly tip it to drink it. You'll then see an ellipse, tip it more, then a parabola, hyperbola, line, and then finally a point. And then empty set. And so you'll go through all of the all of the conic sections by looking at some sort of liquid inside of a martini glass. It has to be a martini glass because it has to be conic. So some sort of conic, something where you can, it looks like a cone. So you can look at it. Okay, so let's go over section 7.1. That was a quick intro. And of course, if you actually look at your book, they have better pictures than what I've done. So they've actually done it with a computer. So their drawing looks better than what I have done. So section 7.1, circle and the parabola. Okay. So, well, actually, I guess I should also say that in general, we can generate all of these objects by looking at a, oh, maybe I'll write it this way, by looking at the solutions to a quadratic in two variables. And so ax squared plus bxy plus cy squared plus dx ey plus f equals 0. So if I look at any solution of this equation, it turns out to be one of these conic sections. So the solutions to this quadratic equation in two variables will give you one of the conic sections that I've drawn. Okay, so first, a circle. A circle is the locus of all points equidistant from a fixed point called the center of your circle, and that fixed distance is called the radius of your circle. Suppose you have a circle centered at the origin of radius r. Then, by Pythagorean's theorem, a squared plus b squared equals c squared. So the equation of a circle centered at the origin of radius r will have the form x squared plus y squared equals r squared. If instead you had a circle of radius r centered at the point h, okay, then the standard form for the equation of a circle centered at hk of radius r will have the form x minus h squared plus y minus k squared equals r squared. Okay. A parabola. Let's draw a line. I'll call this line the directrix. Draw a point. I'll call this point the focus. A parabola is the locus of all points equidistant from a fixed point called the focus, and a line called the directrix. So if I take any point on the parabola, then these two distances are the same. The distance from this point to the focus is the same as the distance to the directrix. If I take a line passing through the focus perpendicular to the directrix, that is called the axis of symmetry. Your parabola is symmetric about the axis of symmetry. If I take a point on the parabola intersecting the axis of symmetry, this would be called the vertex. Let me determine the equation of the parabola. So let us suppose we have the following. That the focus here is at the point 0p. I'm not assuming p here is greater than 0. I've just drawn it as if it were, but I'm not assuming that it's greater than 0. And suppose that the directrix is the line y equal negative p. And so the parabola is such that its vertex is at the origin. Okay. Now, suppose I take some point xy on the parabola. Then this distance must equal this distance. And so these two distances are the same. By definition. Well, this point here on the parabola, I can figure that out because, well, it has the same x-coordinate. And the y-coordinate, well, the y-coordinate is negative p because that's negative p there. So I'll use the distance formula. Recall the distance if I have 2 points, x1, y1, well, maybe I'll call it q, x2, y2. Then the distance between these points is just the square root x1 minus x2 squared plus y1 minus y2 squared. Of course, I could have written it the other way around, x2 minus x1 squared plus y2 minus y1 squared. Okay, so let's find the distance from this point to this other point. So it's the square root of x minus 0 squared plus y minus p squared. And the distance of the other one is, well, x minus x squared plus y minus a negative p squared. Square both sides of the equation, and so you get x squared plus, let's multiply this out, y squared minus 2py plus p squared equals 0 squared plus, well, y squared plus 2py plus p squared. Subtract out the y squares, the p squares, add 2py to both sides of your equation, so you get x squared equals 4py. That is the equation of a parabola. Okay. Now, of course, this is where you have the focus is at 0p. The directrix is y equals negative p, which of course also implies that the vertex is at the origin. Now suppose I have the equation of a parabola. Let's do it again where the vertex is at the origin, but the focus is at, let's say p0. And of course, notice that if p is greater than 0, this parabola points up, and if p is less than 0, this parabola points down. Okay, and suppose the directrix is x equals negative p, then the equation of your parabola is y squared equals 4px. So all I'm doing is interchanging x and y. Let's do another equation. Suppose your vertex is at hk and the focus is at, let's do this one first, h k plus p, and the directrix is at y. Y equals k minus p. Then the equation of your parabola is x minus h quantity squared equals 4p y minus k. And suppose you have your vertex at hk, the focus is at h plus pk, the directrix, and of course, I guess I should have said this. If p is greater than 0, then it opens to the right. If p is less than 0, it opens to the left. Of course, this is the same as the above one. If p is greater than 0, it opens upward. P less than 0, it opens downward. Okay. So the directrix x is equal to h minus p. Then the equation is y minus k squared equals 4p x minus h. And if p is greater than 0, it opens to the right. Less than 0, it opens to the left. Okay. Okay, so let's do some examples here. Oh, maybe I should. Maybe I should tell you that too. if you take a line parallel to the directrix passing through the focus, so let's see, green. If you take a line parallel to the directrix passing through the focus, this is called the lattice rectum. Okay, and of course half of it is called the semi-lattice rectum. So let's do on page 666. Let's do problem number, general form too. I didn't say what general form is. Okay, so let's do problem number 18. I have the following. Circle. So it says 5, 4. The center, which I usually call C. I'm going to call it C. And -2, -3. Write as an equation. Write an equation of the circle shown, and write your answer in standard form and then in general form. Okay, so first off, let's figure out the center of my circle. So to figure out the center of my circle, I notice that if I have a diameter, I forgot to call it, well, for a circle, if you have a line passing through the center, then this is called a diameter. And you notice that the center is at the midpoint between the midpoint of the diameter. Okay, so let's recall the midpoint for the points x1, y1, x2, y2 is just x1 plus x2 over 2, y1 plus y2 over 2. It's just the average of the x and y coordinates. And so the center of my circle will be 5 minus 2 and 4 minus 3 over 2. So 3 over 2 and 1 over 2 is the center of my circle. Therefore, the equation of my circle is, well, x minus 3/2 squared plus y minus 1/2 squared equals r squared. I don't know what r squared is yet. Let me plug in. I can plug in either of these 2 points. Probably the point 5, 4 is easiest. Let's plug in 5, 4. So 5 minus 3 halves squared plus 4 minus 1 half squared. So r squared equals 7 halves plus 8. 7 halves again. Really? Let me check that. 10 minus 3 is 7. 8 minus 1 is 7. Yeah. So this is 49 over 4 plus 49 over 4 is 49 over 2. Okay. And so the equation of my circle is x minus 3 halves squared plus y minus 1 half squared equals 49 over 2. So this is in standard form. The general form, well, you multiply it all out, and you get it looking like a quadratic like I wrote at the beginning. So let's multiply this out. So I get x squared minus 3x plus 9/4 plus y squared minus y plus 1/4 equals 49 halves. So I have x squared minus 3x plus y squared minus y plus 10/4 plus 5 halves equals 49 halves. So let's subtract 49 halves from both sides. I give you 44. So I have x squared plus y squared minus 3x minus y. Writing this in descending order, lexicographic ordering. Minus 3x minus y. 45 minus 49 is a negative 44 halves, which is a negative 22, equals 0. And so this is now the equation of your circle in general form. Like what I wrote at the very beginning. Okay, let me do problem number 30. Y plus 1 squared is equal to 28 x minus 2. Okay, so it says find the vertex, focus, and directrix for each of these. So first off, I have that 28 is equal to 4p. So p is equal to 7. The vertex is going to be, well, at 2, negative 1. The focus, well, you notice here that the one that doesn't have the square is the x. So to this x here, I'm going to be adding 7. So that'll be 9, negative 1. The directrix, well, I'll be subtracting 7 from this 2. Oops. I said it wrong. And so I have here that x is equal to 2 minus 7, negative 5. And that is the vertex, focus, and directrix for that parabola. Let me do problem number 32. The vertex is at the origin. The focus is at 0, negative 3. Find an equation in standard form for the parabola. Okay, so I have here x squared equals 4py. Since the vertex is at the origin, I don't subtract anything from here. Since the focus was found by doing something to the y, so I have that x squared is equal to this. So now let's figure out what p is. Well, from here, from the focus, I see that I'm subtracting 3 from the y coordinate, and so p is equal to negative 3. And so I get x squared is equal to 4 times negative 3, negative 12y. And that is the equation of my parabola. Okay. Let's do problem number 42. The vertex is at 3, 5, and the directrix is at x equals 6. Maybe I should draw this. So let me, oops, I don't need that room. So let me just give you, maybe I should have drawn this too. Just very. Okay, so the vertex was at the origin, focus was at negative 3. Okay, so it means that it looks something like this. And so, yes, that's correct. Now let's do this guy. X equals 6 is my directrix. And at 3, 5 is my vertex. So we're around here. And so my parabola looks something like this. Oh, so this is going to be y minus k squared is equal to 4p x minus h. So that should be the form for the equation of my parabola. And well, I have that x is equal to 6. Well, that means the directrix is the form. Well, x is equal to 3 minus negative 3. Okay. And so that means that in this case, p, so remember that so here's my distance here. And the distance here that I've gone is, well, uh, to go to this distance here is, it says is, well, this is 6, right? And this guy here is a 3, 5. So it said this distance here is 3. But notice that you're going in to go to the vertex, you're going in a -3 direction. So this has got to be a -3. So P has got to equal -3 because you're going in, instead of going to the vertex, from the vertex to the focus in a positive direction, you're going in a negative direction. Okay, so let's do this. So Y minus K, 5 squared, equals 4 times P. Well, 4 times 3 is 12, -12. X minus H, which is 3. And that is the equation of your parabola. Okay. So that finishes off section 7.1. And I guess that's it for today. Stop. Okay, here, wait. Okay, let's see if I can, maybe I'll, 7.1. Okay, good.